We're going to talk about the different constant volume reactors, but also variable volume ones. Yeah.
If we were indexed by J,
Yeah.
then shouldn't we have like numerical indications for each species as opposed to letter ones?
You could probably argue that to be true, but Fogler is Fogler, and I wasn't going to change the entire nomenclature of my notes and Fogler, right? And also, the numbers are usually used for steps, right? We use those for reaction steps. So.
But when you set up a summation, you go index like from A to J or something, or A to Q or whatever.
Your summation is from J is equal to species 1 to species whatever. I mean, think about it more like programming, right? You can loop through a number of strings just like you can loop through numbers. You don't have to go 1, 2, 3, 4. You can loop through A, B, C, D. That's fine. So you're just looping through every species in your system. Whether you call that species A or species 1 makes no difference. Okay, so what systems might be constant volume? Since we kind of brought it up. So if I'm doing a gas reaction in what type of vessel? In a batch reactor, but closed, rigid. That's maybe the word we want to use, right? In a rigid vessel. If I'm doing it in a balloon, volume's going to change. It can change. If I'm going A to make 2B, then as I do the reaction, I'm making more gas molecules, so the volume increases, right? So yeah, a gas reaction in a rigid vessel. What else? What if you guys were in general chemistry and you're doing your lab? You do it in a beaker, right? Is that beaker rigid? Not on top. Does it matter? Yeah, I mean you're around it. It's because it's a liquid. Reactions are typically, not always, and that's both because liquids are generally not that compressible and because you might have a lot of solvent present, so the change in density is not going to be very appreciable. So yeah, a gas reaction that's in a rigid vessel, most liquid phase reactions, and then what about a gas reaction like this? Would I experience a volume change for that reaction? Maybe. Why maybe? Not for ideal gases, yeah. And what about this? Yeah.
Can I ask you one quick question on volume? Sorry.
Yeah.
You wrote everything over V0, right? Which is the initial volume of the total system?
Only if you're at constant volume.
But wouldn't it have to be over the partial volume of each component?
No, because I'm trying to write it in terms of concentration. So it's not density, it's not the molar volume of a species, it's simply the concentration of that species. Right? It's the total volume. If I add some inert, it still dilutes it. So again, I'm trying to write it in terms of concentration, not like molar volume, which would be, you know, the appreciable amount of volume that that's taking up.
When you wrote volume of C as a function of X, you had the volume of C over the total volume without using concentration to use theta, which was a molar term.
I don't know which equation you're looking at.
You said VC of X would be equal to theta C times 1 minus X over V0.
All right, let me put these back on the board. clear? All right, so I'm not sure which formula you were talking about.
Is that what the formula about how volume varies with X?
I haven't said how volume varies with X. I just said that V can be a function of X. This isn't multiply. This is just saying that V, it can be a function of X. But we haven't talked at all yet about how volume can vary with conversion. That's where we're headed. Okay, so for this reaction, would we expect a change in volume?
Quickly, shouldn't you write 4 ideal gases, not the not?
Yeah, I mean, I'm trying to say no delta V for ideal
Still
gases.
want confusion.
Yeah. But yeah, A to B versus 2A to B plus C. Would I get a change? No. So generally speaking, right, we just define this delta term. If delta equals 0, then we have a constant volume system, yeah.
I'm just checking, so for theta like B and theta C and theta D, would that just be the concentration of one over the concentration of other?
It's the
other?
initial concentration.
Yeah, the initial concentrations? Okay.
Yeah, moles.
Yeah, it's moles because you would measure the concentrations and then divide because
Yeah,
the
yeah.
V's cancel out,
Yeah, the
right?
V's would
Okay.
cancel out, but
That's
yeah.
why I was just wondering like how you found the like
Yeah.
experiment.
All right. So those are the 3 types of reactions that are going to be constant volume. Gas reaction in a rigid vessel. Liquid reaction, you would typically assume it to be constant volume. Okay, so if you're not given any information except that it's liquid, that's a safe assumption to roll with. Gas reactions where delta is equal to 0. So if we go back to this one, if I have a gas reaction in a rigid vessel like A goes to 2B, what happens as conversion changes? Does volume change?
No pressure.
Pressure changes, right. So another way to say that the volume is not changing, I mean, that the volume might be changing, if you see the words constant pressure, that might be a hint that the volume's changing to alleviate that pressure change. And again, I mean, you can certainly imagine a reaction taking place in a balloon or in a piston. In reality, those things aren't very common. I mean, obviously car reactions, you know, automotive reactions do take place within pistons. That's how it gets the mechanical force out of it. More specifically, though, in this class, the systems where you're going to have volume change are in flow systems, right? Because there's nothing holding it, so the pressure is going to be constant and the volume will change. And that's what we're going to go into next. Okay, so generally speaking, when I go from a batch system to a flow system, I'm replacing we don't talk about number of moles in a flow system, right? We talk about molar flow rates. Okay? And so again, you can replace the number of initial moles with the inlet flow rate to whatever your flow unit is. If I want this concentration at a specific point, that's the flow rate of that species, not divided by volume this time, but instead divided by what? Volumetric flow rate, yeah. Booklet uses like a little v. I'll try my best. It'll look something like that. So that's in units, right? That has units of moles per time. And this is volume per time. So you get moles per volume, which is concentration. All right, everybody see that? It's the volumetric flow rate now, not the total volume, because we're dealing with a flow system, not a batch system. Yeah.
Can we differentiate our variables like with like superscripts or something, like with some sort of symbol like where you like a bar or
V
a
dot,
or a
V
dot
dot.
for
V
time
dot.
variables
V
like
dot.
that?
V
So we just keep track of time variables differently.
No, the dot at the top.
No, like bit V with a dot on top.
Yeah.
Yeah.
If the book uses it, stick with the book.
I'll use a little v with a dot, but yeah, no complaints if you're like, I couldn't find little v dot in Fogler. Sorry, you guys asked me to change it. But I'll try to do that. It is a little v though. I mean, it's a script v in Fogler too. Like, it's pretty obvious in the book, but I can't write as well as the book can print. All right, so the stoichiometric table for a flow system. Let's come over here. This is why we've been saving it. What do we change? Instead of in, it's F, right? It's all that we've done here. This same thing. Okay? And we'll just do one more change over here is, I'll remind you about the big theta, right? We didn't put that on here. We could have when we did the first table. But with big theta, we can write this now. FA is equal to that. FB is equal to now FA naught theta B minus B over A times X big theta. Trying my best on that. Is that clear to everybody? All these equations work, whether you're dealing with a flow-based system or a mole-based system. Nothing changes until you start talking about concentration, and then things get just slightly different. Instead of dividing by a total volume, you have to divide by a volumetric flow rate. So again, units will set you free, right? If you try to divide by the volume of a CSTR, you're going to realize that you've got an extra time in your concentration. Concentrations are not per time. They might change with time, but the units on concentration are simply moles per liter. So you are going to sometimes have volumes, right? We've talked about the volume of a CSTR and the volume of a PFR. Just because the volume is in the problem doesn't mean that's what you divide by. You need to think about the volumetric flow rate. And again, using the equation, using delta that we defined earlier, we can say the total flow rate of all species is just equal to the total flow rate of all species coming into the system plus delta times the initial flow rate of A times the conversion. There's no change in density then the volumetric flow rate's not changing. That's not always true. I'm saying that's true if there's no change in density. Again, we're going to talk about systems where that's not true here in just a second. So going back to our equations that we had earlier, right? CA is equal to FA divided by the volumetric flow rate, which is now equal to CAO times 1 minus X. I'm just taking the formula for FA from that table and plugging it in, right? Yeah, thanks. It's the theta is what makes it AO.
And that's a plus, right, for C?
Yeah. So you might notice that I've already written these on the board today, right? So if I'm writing concentration as a function of X, does it matter if it's a flow system or a batch system if the volume's not changing or the density's not changing? No, you get the same equation, right? Again, it's only true if the volume's fixed in the batch system and the density is fixed in the flow system. Then you, luckily, get the same equations. There's this big figure in Fogler's book. Sorry I don't have the table, the page number, but it's in chapter 4. And it basically says at the top, gas, liquid. And then it says batch, flow. And you can just follow these arrows and eventually it leads you to the correct equation. Okay? All right, so now systems with volume change. So when we're talking about systems with volume change, we're usually talking about what types of reactions, gas or liquid? Gas. So if I have some gas, how do I relate, what is its volume in terms of number of moles?
Oh, is it using P equals NRT using the start?
Yeah. So again, we're going to start with, left out. So what is Z?
Compressibility.
Yeah. And as you might guess, we're going to generally assume that the compressibilities are equal to 1, or at least that they're not changing. Okay, so why is it NT? You guys used to write just PV equals nRT. Right, don't just put in any number of moles, right? You got to put in the total number of moles in the system if you're talking about the idea of gas law. And you're talking about things like total pressure, right? This is the total pressure, not a partial pressure, so that's why you use the total number of moles. Okay, and then at T equals 0, we're going to say P0, meaning initial pressure or inlet pressure, either one. Why isn't it R0? Yeah, isn't that nice?